All right, so we're looking for an endothermic, and we're going to label a bunch of things on this progress diagram. So we're going to like this and say time and energy and endothermic, so something like that. And we've got reactants and products, and we've got amount of activation energy, and then we've got a delta G value here, and then this section here is our transition state. And am I missing anything? And this is endothermic because the delta G for this is positive, right? So this is going to be a process that requires energy to occur, otherwise it'll stop. All right, so we want to calculate the rate constant and determine the rate law. Okay, so if I pick trials 1 and 2, what information do I get? 8?
I mean A.
Yeah, A, yeah. So here it goes up by 1.5. We okay with that? How much does it go up here?
0.5.
Yep, 1.5. If I multiply the 0.26 times 1.5, I get the 0.39. They're all 13s, right? 2 26s is a 13, and a third 13 is 39. Okay, so they both went up by the exact same value. So what order is it with respect to A? First. Okay, so it's first order with respect to A. And then let's try trials 1 and 3. So from 1 to 3, I get no change for A, and for B, I get a change. How much of a change is that? I got 4, 3, and 2. How about 3? Yeah, 75 cents times 3, $1 or $2.25. So this goes up by 3, and how much does this one go up by? How much does that go up by? By about 10? All right, so this goes up by about 10. Okay, so 3 is equal, dang it. What is that? I don't care. 3 is equal to 10 when what is the exponent there? What exponent do I need? I'm going to put a 3 here. Sorry, I'm not going to put a 3 here. I'm going to put a 2 there. So 3 squared only gets me 9, right? Is that okay? It's this is all experimental data, right? So do you think it's going to nail it dead on like it did with the first one all the time? Now there's going to be a little bit of wiggle room with this. So what you're going to do is pick the closest whole number exponent that gives you about what you're looking for. So it'd be second order with respect to the to B in this case. So now I have to figure out what the rate constant is. And so the rate law itself is going to be, that's driving me crazy. Rate is equal to the rate constant times A to the first and B to the second. So the way we're going to calculate K is I'm going to solve for K. Particularly bad today. What just happened? Okay. So K will be equal to rate divided by A to the first and B to the second. And so I can pick any trial that I like and just plug numbers in. So I'll pick the first trial since whatever, it's the first one. And so K will be equal to 0.26 times 10 to the negative ninth divided by 0.002 times 0.000755 squared. And we just solve that. Dang it.
Can you scroll over a little bit?
Oh yeah, sorry. Where's the mouse? Alright, so I got 0.26 E negative 9 and divided by 0.002 and divided by 0.00075. Alright, so I got how many numbers? Two. So I got 1.9 times 10 to the fourth. Alrighty, let's do that same thing again with another one of these. So I'll pick trials 1 and 2, A doubles and B doubles. So this goes up by 2 and this goes up by 2, so it's first order with respect to X. And then what's tricky about Y? Yeah, this exponent goes to a 1, right? So this is 0.1 or 1.6, but really if they have the same exponent, it'd be 16. So this actually does double. And I don't know what happens here. .35 divided by 0.0438. So this goes up by about 8. Okay, so I've got something that's a 2, and then my answer is 8. So what's the exponent? Are you good with that? So third order, and so I've got rate is equal to K, X to the first, Y to the third, and K is equal to, I'll pick the first one again, 4.3 times 10 to the negative second divided by a little 0.0014 times 0.08 cubed. Alright, so 0.043 divided by 0.0014 divided by 0.08 cubed. I got 6 times 10 to the fourth. Alrighty. So I want to make a battery here, and it's a zinc magnesium battery. And calculate its voltage and talk about oxidized and reduced. Okay. So I will draw a beaker. And I'll draw another beaker. And I'll draw
a salt bridge, and I'll just put, I don't know, potassium chloride inside of the salt bridge. And I got a liquid level here. And what do I got? Magnesium, and I got zinc. Actually, it doesn't really matter what side I put them on, so I'm going to put my magnesium right here. And I'll put a zinc bar here. And in here I'll put magnesium ions and, I don't know, chloride ions. In here I'll put zinc ions and chloride ions. And then I got a wire going from here to here with a voltage. And which direction are the electrons going? So let's go to the notes. Scroll down here. I'm looking for magnesium and zinc. So there's my magnesium, and then there's my zinc. So magnesium is higher on the list. Alrighty then. So we'll jump back over here. And so since magnesium is higher on the list, the electrons are going to go from the magnesium to the zinc. And there's going to be a buildup of zinc on this bar here. And there's going to be a chewing away of the magnesium on this bar here. As these zincs grab the electrons and attach themselves to the bar, and these magnesiums lose electrons and turn into magnesium +2. So we want to calculate a voltage. So the two half reactions are magnesium solid is turning into magnesium aqueous +2 electrons. And we got zinc aqueous +2 electrons turning into zinc solid. So the shorthand notation for this is magnesium solid, magnesium aqueous, and zinc aqueous, and zinc solid. And then we need voltages. So the magnesium is going to be probably consuming voltage. So this is not what's happening for the magnesium, right? The magnesium is actually doing the exact opposite. So the voltage for the magnesium isn't -2.38, it's 2.38. So my magnesium is going to be generating, so this guy here is going to be generating me 2.38 volts. All right, so now let's check my zinc. My zinc is here, and that is what's going on, right? That is the correct direction, so we will use that negative. So then the zinc is a negative 0.76 volts. So then I just take those guys and add them up. And so I get a 2 and a so 1.26 volts. Would that make a good battery? Jeez. No? That would make a good battery? Remember the batteries for the calculators? Those 9-volt or those AA batteries? 1.5-ish, right?
2 negative 76?
Why?
Isn't it 2 electrons?
2 electrons, but both of the electrons are being consumed by the same atom.
Oh, by the same.
Yeah, 2 electrons are being used, but the reason that we needed to do it twice with the silver last time is because each silver could only accept 1 electron. So this is actually saying you get this voltage and you get this voltage if he gains 2 electrons or he releases 2 electrons. Who's being reduced to, so whose charge goes down? The zincs, right? So the zinc is reduced. And so who's oxidized? Magnesium is oxidized. Now, when the zinc was reduced, what did it do? What did the zinc do to the magnesium? The zinc stole electrons from the magnesium, right? And that process is oxidation. So the zinc is actually the oxidizing agent. So the zinc said, hey, I'm taking your electrons, so I'm oxidizing you. Well, the magnesium actually didn't want its electrons. So the magnesium was like, hey, take these things. I'm going to reduce you. So then that means the magnesium was the reducing agent. Okay. Will electrons be transferred for these different situations? Okay, so I have magnesium metal and mercury ions. So this magnesium has its electrons, and this mercury is missing electrons. So will a reaction happen? Yes. Magnesium is higher on the list and it has electrons. The mercury is lower on the list and it's missing electrons. So electrons will definitely be transferred from the magnesium to the mercury. All right, so will electrons be transferred with zinc and copper? So I've got zinc, aqueous, and I've got copper, aqueous. So are there going to be any electrons transferred? Copper's lower on the list, so is zinc going to give its electrons to copper? It can't. It doesn't have any electrons, right? See its charge is +2? That's it. It already gave them away. Will electrons be transferred from calcium metal to lead metal? So this is calcium solid, and will it transfer it to lead solid? So calcium's higher on the list, so will it give its electrons to the lead? Calcium has electrons. Nope. The lead doesn't need any electrons, right? Since the lead has all of its electrons, it can't accept any more electrons. Metals can't become negatively charged. So if you're solid, you've got them. And so even if you would need them later on, you can't get them. So this reaction, there's not going to be any transfer there either, because no one needs electrons. Will the electrons transfer if you have silver metal and sodium ions? Okay, so I've got Ag solid and I got Na plus aqueous. So the silver has electrons to give. The sodium could use some electrons, but will the silver give its electrons up to sodium? Nope. No. So there's no reaction occurring here, and the reason is that the silver is lower. So it likes to hold on to its electrons more than the sodium likes to hold on to its electrons. Okay.